Hello reviewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about hydrothermal liquefaction or HTL. So let's dive deep into it. So here's the deal, there's a problem, and ironically these problems are the same thing, as in we have a lot of organic waste, as in gigatons of it worldwide, and we generate it regularly, as in it's like, okay, boof, you kaputed 10,000 tons of organic waste, 5 minutes later, sir, more. And not to mention, because of the amount and concentration, it is very hazardous. You can't just let it go. Like, you have to process it, not only just like handle it, you have to process it. You can't just like, okay, I'm gonna dig a pit and dump it there. Yeah, it's too dangerous for that. So that's a problem on one end. Second end, we need liquid fuel. No matter what anybody tells you, you cannot fly a jumbo jet even on liquid hydrogen, let alone on a battery. It just won't work. Like, if you have a flight that goes from continent to continent on like decent speed with decent payload, yeah, that's not happening on a battery. And if somebody figured out a battery that is that level energy dense, you may not want to be in the same continent as it. So fundamentally, as of now, we have organic waste and we have a requirement for liquid fuel that cannot be, you cannot do anything to it, practically speaking. So here's the deal. What if you look inside a bio waste? For example, let's just say you are looking inside a stuff. Let's say it has a lot of lipid. What does that mean? That simply means they are giant fatty acid bounded by glycerol. You look into glucose, sugar. What is it? It's basically hydrocarbon with a lot of oxygen. You look into fatty acid or you look into other stuff. Most of it is hydrogen and carbon, most of it. Of course, let that be very clear. There is some places where you have nitrogen, you have a lot of places where you have oxygen, but core component, fundamentally, if like you blur your eyes, it's hydrocarbon. You look into wood, I'm talking like full-fledged wood, it is cellulose. What is inside the cellulose? Hydrogen, oxygen, and carbon. Basically, hydrocarbon which has oxygen. So fundamentally, bio-waste, all bio-waste, including plastic, is a mixture of oxygenated hydrocarbon. Like, of course, there is some contaminants, there is this on that, there is no discussion about that. However, core is always hydrocarbon. So what if we can mix together? What are we doing? Like, fundamentally, what are we doing when we are drilling on Earth? We are trying to get a biocarbon, as in hydrocarbon that has been cooked by nature. We have a waste that has hydrocarbon. What if, instead of waiting Earth for millions of years of cooking time, what if we did the cooking? So that's the fundamental problem. Look into all organic waste, more or less there will be hydrocarbon in some form or the another. It's just how easy it is to extract it, or hard. So HTL. So Friedrich Brigham, I'm sorry, I'm very bad at pronunciation. He founded this technology in 1913, got a Nobel Prize for this in chemistry in 1931. So it's an ancient technology. And the idea is fossil fuel formation is the same thing. You take a biodegradable material and you just cook it under pressure and temperature. He just figured out, instead of taking millions of years, what if you do it in minutes? What if you're like, hey, give me 30 minutes with this waste and you get crude oil. Done, go home. He's like, I got this. He figured it out. And what are you doing for that? Cooking. Well, nothing too extravagant. That's why it was done in 1930. Water and lot of pressure. That's it, nothing fancy. And you do need subcritical water, as in water that is under so much temperature, it's about to boil, but you are pressurizing it. So this could be 280 degrees Celsius to 350, a little bit more degrees Celsius, and it cannot boil. Let that be very clear. Like, how the heck that can be? Well, pressurize it. But we are talking about serious pressure. Let that be very clear. This is an industrial thing. So pressure could be 165 bar. If you want PSI, that's a 2400 PSI kind of deal. Now let that be clear. This is generally the upper range. Generally, you do not need to go that high, but if you are dealing with certain stuff, you may need to. So this is how it works. Now here's the, how can you digest so much? Almost all organic waste, be it wood, be it lignin, be it basically hydrocarbon, be it microplastic. How? Well, physics. In physics, if you look into water, water is not just water, H2O. It's not just that. It is basically H plus and OH minus. Now, what happens if you agitate it? Basically, when you electrolyze it, what the hell you are doing? You are doing this. You are creating acidic H and base OH. Somebody figured out this same thing happens under thermolysis also, as in you heat this puppy up under high pressure, concentration of these things, these ions become extremely hot, as in it goes from universal solvent to universal turbo solvent. Once you have this high enough concentration, you have base and you have acid attacking from both sides, nothing can handle it. Basically, you took a universal solvent and you just made it nitro booster charged. And add some catalyst to it. Again, catalyst will not be consumed for tuning of the crude oil output. As in, you can even have coal and make basically oil out of it. That can be done. Now, biggest benefit of this advantage of going YOLO on pressure and high temperature, this is the omnivorous waste digester. As in, can humanity break down organic waste and get useful stuff? Yes, we do that. It's called basically biodigester. You put in cow dung and you get CH4, natural gas, methane on the other end. Great. Problem is, it's very finicky. As in, you're like, hey, we have human waste, more than enough human waste. Why not we just use that same thing? It requires a different digester. It's like, okay, we have one digester for cow dung, you have another digester for human waste, another digester for food waste. If you mix all of them together, yield will go down at best. At worst, the system will stop working, because biology is very finicky and it takes time. It takes upwards of 30 days on a large tank to like break it down and actually give you yield. This puppy works in 15 to 20 minutes, 30 maximum. So that's the fundamentally crucial aspect. And one of the unique abilities, the best way to handle plastic is pyrolysis, cook it. But that assumes you have dry plastic, as in the plastic is just raw plastic. Awesome, perfect. You do not need high pressure, mild temperature, good, take it and go. But what if plastic is mixed? What if you are trying to clean sea and you have rivers, you want to clean that? That's wet plastic. And if you try to dry that plastic, yeah, that will take so much energy, you won't be able to do it economically. This puppy digests it. It's like, I do not care. I directly drink it. So fundamentally, it can handle wet management directly, and even plastics also. And speed is rapid. Instead of days, it's minutes. And the output you get is the same three things. You get some amount of gas, as in some amount of methane, most amount of carbon dioxide, serious amount of hydrogen. Sorry, I am saying hydrogen, H2O. And these are generally the gases that you're gonna get. And then you're gonna get bio crude, as in like crude oil. And then you're gonna get basically solids. That solid is used as a fertilizer. So this is HTL. You're basically turbocharging nature. Okay, that's the idea. How the heck you physically build it? Well, you start with your feed tank. Be mindful, this must be wet, because you have to supposed to pump it, this puppy. So you're gonna have a high pressure feed pump, you pump it. Generally, it goes through a heat exchanger. Because again, primary energy consumption of this puppy is not the pumps, is the heating element, because this is endothermic. This puppy consumes energy. Every time you're taking a long hydrocarbon chain and you're attacking it, breaking it, fundamentally that consumes energy. So it's not like, okay, I heat it up, get it to temperature, then insulate it, it will be fine. No, you have to keep heating it up because it's consuming energy. So you do need to heat that up. Now, once you do that, once you do the processing, the byproduct still has a lot of heat in them, like a lot of it. So the idea is you send it through a heat exchanger. Heat exchanger heats up the incoming feed, and benefit of that is your electrical consumption for a large plant goes from megawatts per hour to 1 or 2 megawatt per hour. Like drastic thermal energy consumption goes down because of recycling of the system. So you have heat recycling, you have electric heater, and then the processing happens in generally plug flow reactors. There are other designs. This design made sense to me, the cheapest one. The idea is if you try to do it on a big tank, does it make sense? Of course you can do that. It's just that cost of that tank would be painful. Why? High temperature steel tank, that's minor inconvenience. High temperature tank that can also handle high pressure, that's bonkersly expensive. That's autoclave territory, as in don't ask the price. And again, because you have such a high acidic and basic environment, basic pitch tool steel will not work. You have to have a very brutally robust steel to handle it. So people generally use pipes. They are much cheaper to make for robust PSIs, and you have a plumbing like this, going serpentine plumbing. And generally you coat it with an electrical heater, and then you have insulation going around it. So you generally insulate it, heat it up, put it under high pressure, and it only takes 30 minutes, meaning once you have feed going in, the feed will start, output will start happening in 30 minutes. 30 is also, that will be the first time. After that, it will be very quick. So processing speed is also high. So, and what is the output? Well, generally the output in this phase is liquid. It's mixed of everything. You had high pressure temperature environment. You're not going to get clean separation. So after you had heat exchanger take most of the heat away, it goes into separator. Separator is the old school separator where you have things finally relaxing, gases gets into gas phase. Be mindful, some feedstock can give you enough methane that you can help you use that methane as a burning fuel and help offset the heat cost. Generally, it will not give you enough to completely eliminate the heat cost, but every little bit helps. Otherwise, you have to figure out to store it or do it, or just worst case scenario, just burn it away in a flare. So might as well use it for heating. So you have gas, you will have carbon dioxide, and you will have water vapor in that. So that goes into gas phase. This liquid, now the temperature has come down because again, you cooled it via the incoming feed, the liquid will settle down. Water is much denser than oil, and voila, biocrude travels on top and it floats into the second phase. You get biocrude, you get aqueous phase. Now this aqueous phase is the reactant that happened here. You cycle it again. So water consumption goes down drastically. This is not a continuous drinking water process. Heat consumption and water consumption can be very significantly minimized. I've seen 1 or 2 designs where they just use solar concentrator to, again, solar water heater is not hot enough. Concentrator is hot enough to just like, there is no heat consumption, and water is cycled well enough where it's like you don't have to worry about it. So aqueous phase loops back the system, and if anything was unreacted, next time it will be reacted. So this is the physical design of it. Not too complex, fundamentally speaking, not too complex. Like compared to a biodigester, this puppy is dead simple. Now what about tuning? Well, input dictates the output, so to say. For example, computer rule applies, garbage in equals garbage out. So human sewage, let's just say you are taking a city's sewage and you sent it through it, you're gonna get a very oil that is very thick and it has toxification of nitrogen and sulfur. Basically that crude will have way too much nitrogen and sulfur to deal with. But what happens if you, same process, same plant, you send it wood, you'll get very oxygenated biocrude. Why? Lignant have way too much of that. So of course, majority of it will be broken down, but not all of it. So that will have rich bio, meaning it will require post-processing. So it's like every other chemical process, input dictates the output. And then people generally add stuff to it. For example, you can add sodium carbonate to it, especially if you are dealing with wood, and that will increase your oil yield. More things will convert into oil rather than converting into sludge, because again, your key is getting oil out, not gases, not solids. The aim is to get the oil as much as possible. Some solids will be there because of, let's just say, what if heavy metal went inside? Metal will not care about 300 degrees Celsius. It will just come out on the other end. You do not want that to be in the liquid or gas. Thankfully, it cannot go into gas, but it can mix into liquid. Thankfully, the system, how it is designed and how it works, it generally settles out with a solid waste part of it. So that's how you optimize the system. You can have nickel catalyst, especially if you're trying to make basically seaweed biofuel or algae, you're trying to handle with that. In those sort of scenario, that will allow you to break down basically nitrogen and sulfur. So that concentration will go down into your crude oil, and having lower concentration means it's much cheaper for refineries to handle it. They will be very happy to pay you a premium for that. So nickel, and again, nickel is just one metal. There are other metals also. You have temperature as a knob that has to be controlled. For example, you are cooking lipids, as in seaweed, you are requiring 300 degrees Celsius. Cool, fine, fine. Lignant, wood cooking, you may require 350 degrees Celsius. But you were like, hey, I'm dealing a lot of people, and people are on antidepressant or Ozempic and things of that nature. Those are forever chemicals. We need to destroy those. Yeah, your temperature will go up 225 degrees Celsius. So, oh, at that point, it also starts to disintegrate microplastic, meaning it won't be, oh, it is cycling. No, it's destroyed, done, gone, deleted, forever gone. So that's the tuning part of it. So what can we expect in the future? Well, it does break down forever chemical. That was a big hassle. There are other things that can filter it out. This breaks it down. This is like, no. Because again, you're like, okay, what if I do RO? Great. What about the, basically the wastewater? That has the concentration. So this breaks it down. It's like, it takes those long chemical chain, it's like, nopes it. Strong acid, strong base, it destroys it. So that's the good part about it. It breaks it down into its fundamental component, which is far less toxic. So that's the whole thing, meaning you can be dealing with a TROCS, that's a category. You can be dealing with PFAS. It's like, I got this, I digest it. This is almost like how you had basically algae as a filtration system for air, because it has the ability to digest NOx, SOx and VOCs. And it does not just like, okay, I'm going to filter it out. No, it breaks it down, it digests it. Same thing is happening here for the most notorious thing that we cannot do anything about. Microplastic disintegrates. It basically depolymerizes it. Be mindful, the only thing that can do any sort of harm to plastic is ultraviolet. And problem with that is it does break down plastic, but it breaks from plastic into like wall of plastic into smaller chunks of plastic. It's still plastic. This puppy destroys it. It's like done. What happened to that? Oh yeah, it's in hydrocarbon now. We cooked it. So fundamentally best. And the fertilizer that you get out of it, it's safer. That's the most, because again, people have been tracing this, that fertilizer, the pesticides, the forever chemicals, they are getting concentrated in soil. Why? Because most farm basically system where people are doing biodigester, they are cycling it, right? You're getting a fertilizer. Why not use the fertilizer? Problem is fertilizer had all the concentration already there. You did not remove it. You just filtered it out. So it's there. That concentrate is still there. You put it into your soil. Soil has pre-concentration of these sort of forever chemicals or Ozempic or fentanyl. Yeah, that's a problem for us. So in 5-6 iterations, you are increasing the concentration. Basically, you're salting the earth. That's not acceptable. This technology breaks it. It's like, no, gone. Like basically, if done correctly, if you close a human system, this will eliminate it. It's like, bro, don't worry about it. It's gone. Gone. Dust. So if you are collecting, let's say, a lot of, you want to seal some rivers, because again, that's where most of the plastics pollution of ocean is happening. Take care of the water. Now you have wet plastic. What the hell to do? Do it in this, and it will take care of everything. Everything. It will just break it down. And fundamentally, it's a simple technology, meaning biodigester is one of those things that look simple, but to actually get a useful yield, you do require biotechnician and like good understanding, complexity, and not to mention some fertilizers like microbiome, gut biome microbiome sort of things to increase the yield, control the yield, or poisoning also happens in those, meaning for some reason, let's say you had some salt that was put into it, like somebody forgot, let's just say somebody dropped a fertilizer bag into the system. Yeah, the whole system would be deleted. This does not care. It just like deletes it. So fundamentally much more simpler system. And again, 1913, you can't get much simpler than that. So, and it can pay for itself with the crude oil. It will not help us eliminate fuel consumption, but it will reduce it. How much? It depends. That depends how much bioorganics you have, but any reduction is better than no reduction. And again, it's doing double dipping. It's giving you a useful liquid fuel, which is much easier to utilize compared to methane output. And it's also digesting your basically bio waste, and it's giving you sterilized fertilizer, as in that does not have pre-concentration of pesticide, microplastics, and forever chemicals. So it's really good because fundamentally speaking, we need it now. Like it's no longer, it would be a cool technology. No, we need it now. We need it like this. The energy cost of that heat, that can be taken from some waste heat source if you have industry nearby, or you can even use solar concentration, but it has to be done. And because of the process, I'm pretty sure it can be stopped and start. It does not need to be like running 24 hours. So for India, it could be great because again, you do need concentrator. Flat plate may not work. Again, it can work. You have to have very large flat solar panel collector area, and then you have to have heat pumps, 2 stages of them to reach that high temperature. Can be done. Or you can just use a dish sort of collector. They can easily cross 350 without any issue. At that point in time, we only run it when we have to basically have the solar flux. Or you have some waste heat source, go YOLO on it. Heck, it could work as a district cooling system. Take all district heat, have like 3 stages of heat pump. It's cooling the district cooling loop and heating the area, double dipping. But we need it now because again, toxic remediation. Let's look at this is the critical part. It's remediating. It's deleting these things. Not just like, okay, I'm filtering it. Like RO is just like, okay, this water does not have it. This water still has it. It's like, no, it's gone. Done. Humans are amazing. We create problems and we figure out how to solve them. So this was my presentation on basically high temperature liquefaction. Hydrothermal liquefaction. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you have enjoyed it, click the hide button. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me your disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.